So now in this example, what we're going to be doing is using the Navier-Stokes equations in order to take a given velocity field and then find the pressure gradient. So this is um, very similar to, or very similar to your textbook example 4.5, except we're just going to stop after we get the gradient and pressure, grad P. It's also kind of a nice follow-on to the example that's on this channel is a example of the application of continuity, where we were given velocity u and w, and asked to find compatible velocity v based on incompressible continuity. So you can go back and look at that one if you haven't already. Okay, so here we're given a velocity field u, v, w, and we're asked what is grad p. And just first, before we get started, just want to write this out in another form. Just to make sure you're familiar with this, we can write this as v is equal to a times x squared minus y squared times I hat um, plus, sorry, minus 2axy times j hat plus 0 times k hat, or a lot of times we would leave that off. So this is a two-dimensional incompressible flow. And again, you can look at the previous example to see that this velocity field right here satisfies our incompressible assumption. Okay, so we're told here that we're going to assume that Navier-Stokes equations are valid, but let's just write out what our assumptions are. So first, we're going to assume that this is incompressible, although we could actually show it directly from the velocity field. We're just going to assume it here, or assume that we've shown it previously. Second, by applying the Navier-Stokes equations, we're also assuming that we have a Newtonian fluid, meaning that the viscous stress is proportional to the shear rate within the fluid. So then, with those assumptions, we can then write out our Navier-Stokes equations, which will give us the components of this grad P. And so those components of grad P that we're looking for, just as a reminder, grad P, that's going to be dP, dx in I, plus dP, dy in j, plus dP, dz in k. And so our problem essentially is to find these three components, dP dx, dP dy, dP dz. We can find them with Navier-Stokes. So to get started, let's write out the x component of Navier-Stokes. So we're going to have rho, so x, Navier-Stokes momentum. We're going to have rho gx minus dP dx plus mu times d squared u dx squared plus d squared u dy squared plus d squared u dz squared is equal to rho times our total derivative of the velocity with respect to time. And we can write that out as the partial derivative of u with respect to time plus the vective derivative. So this is going to be plus u du dx plus v du dy plus w du dz. What we're going to see here is that a bunch of these terms are going to drop out. So first of all, I'm actually reminded of another assumption we need to make. This is going to be that the gravitational vector is just going to be g times k hat, meaning that gravity acts in the z direction. right? So we're assuming that's gravity acts in the z direction. And since it's normally in the negative z direction, we're going to say this is gravity is minus g times k. Okay, so if we look at this expression here, we see that the x component of the gravitational acceleration, um, this is 0. The PDX, this is one of the things we want to solve for. But now let's look at this viscous stress term. If we take the second derivative of u with respect to x, this is going to be, so let's start writing out our terms here. dp dx plus mu times second derivative of u with respect to x is going to be 2a plus the second derivative of u with respect to y. So if we take the second derivative of u with respect to y, we're going to get minus 2a plus the second derivative of u with respect to z. And we see there's no dependence of u on z, so it's plus 0. This is going to be equal to rho times the u dt, which is 0. There's no time dependence here, plus u du dx. And this is going to be our a times x squared minus y squared times du dx, which is just going to be 2ax, plus v du dy, right? v, so it's going to be minus 2axy times du dy. Du dy is just going to be minus 2ay plus w du dz, and here we're given that w is 0, and so this term is just going to be 0. And so now we can start to write this out and gather this up. One other thing that we're going to notice here is that in our viscous stress term, these things cancel out, so this comes out to 0, and I'm left with minus dp dx is equal to, let's see, it's going to be rho times, we're going to have 2a squared x cubed minus, right, so that just comes from this first term here, minus a, let's see, minus 2a squared xy, sorry, and that is xy squared, sorry, minus plus 4 a xy squared, right, simplifying that last term. Now we can see that when we combine these two together, we'll get our final answer for dp dx. And this is equal to, we can gather some terms out here. It's going to be 2a squared rho times x cubed plus xy squared. So there's our first component, right? The x component of the pressure gradient with respect to x. So now we're going to look at the y components of Navier-Stokes momentum. And we're similarly going to see that the gravitational piece of this is going to be 0. So we'll have rho times gy, which is going to be 0, minus dp dy, which is the thing we're looking to solve for, plus mu, this will be d squared v dx squared plus d squared v dy squared plus d squared v dz squared equal to the acceleration, right? Remember, these are the forces on the left-hand side here. This is going to be equal to m times acceleration. And so this is going to be a total derivative of v with respect to t. So that'll be partial v with respect to t plus the effective component, which is u d v dx plus v dv dy plus w dv dz. See where this is going, I hope. So we're going to drop out terms again, right? So we have rho gy, this is 0. dp dy is the thing we're trying to solve for. Let's look at those viscous terms here. If I zoom out a little bit, we can see that the second derivative of v with respect to x, so if we take the derivative of this once with respect to x, we have minus 2ay. If we take the derivative again, this is going to drop out to 0. Similarly, the second derivative of this term with respect to y is also going to be 0. And there is no z dependence, so this derivative, the first derivative of v with respect to z, is 0. And so the second derivative is as well. Then on the right-hand side, dv dt, we have no t dependence, so that's equal to 0. And then we end up with plus u dv dx. We're going to have to pay attention to that, and v dv dy. We'll get to that in just a second. And then this last term, w is equal to 0, so this is also 0. So I'm just going to copy down our form here. So we have v is equal to minus 2axy, u is equal to a times x squared minus y squared. And zoom back in and work on this. And so now we have minus dp dy is equal to rho times u dv dx. So this is a times x squared minus y squared. Dv dx is just going to be minus 2ay plus v dv dy. So v is minus 2axy, and dv dy is just minus 2ax. Okay, so again, we can simplify those in correct terms. So minus dp dy is equal to rho times, let's see, so we're going to have minus 2a squared yx squared plus 2a squared y cubed plus 4a squared x squared y. And so again, we're going to get something that simplifies dp dy to rho times 2a squared times the quantity y cubed plus x squared y. That's right, this is going to be minus dp dy is equal to that. Okay, so now we have our y component of the velocity gradient. And now we want to find the z component, right? So this is going to be hopefully a little bit simpler. We'll start out here. So now the z component. So once again, we're going to have rho gz minus dp dz plus mu d squared w dx squared plus d squared w dy squared plus d squared w dz squared equal to rho times partial W partial T um, plus U dW dx plus V dW dy plus W dW dz. And now remember that we're given that W is equal to 0, and so a whole bunch of these terms are going to drop out. But let's start over here on the left-hand side. So rho gz. In this case, rho gz, this is not equal to 0, right? Because we assume that we have the g component of, the z component of g is equal to minus g, so that's not going to be 0, so we can't drop that out. But since W is 0, this drops out, this drops out, this drops out, this term drops out, and all of these advective derivative components drop out as well. And so all we're left with to evaluate is this rho gz minus dp dz. And so if we write this out, we're going to say, so we said that g, remember, was equal to minus our little constant g times k, meaning that our gravitational acceleration is in the negative z direction. Right? So if this is our z direction, we're saying that the gravitational vector g points in the negative z direction. And so the z component of gravitational acceleration is negative g. And so we have negative rho times g minus dp dz is equal to 0, because everything else canceled out. Or dp dz is equal to minus rho g. Okay, so we now have three components of our pressure gradient, grad p. We could gather these all together and write it out in vector form. So for example, we could say that grad p is going to be equal to, just scroll up and check out our answer, minus 2a squared rho times x cubed plus xy squared in the I direction, right, or in the x direction. So times the unit vector in the x direction. And then it's going to be minus 2a squared rho times y cubed plus x squared y in the times that j component minus rho gk, which gives us that z component of the pressure gradient. So when we're looking for this now, remember, pressure, even though it's a scalar, when we take the gradient of pressure, we end up with a vector. And since in this question we were asked for a vector quantity, the proper answer should give all three components. And either form that I've shown here in boxes would be fine. So you can either show this as the three components individually, right, x, y, and z, or write them all out together, and that would be correct. Another thing that I want to note here is that in this problem we had the velocity in z equal to 0, and so our pressure gradient in z is just this minus rho g. This should look really familiar to you, because this is essentially what we would get for the fluid static condition as well, right? So what we're basically saying here is that the pressure gradient in this fluid, the total pressure gradient in this fluid, in this case, it has a component that varies in x and y due to the flow. And then because W is equal to 0, and this was just a two-dimensional flow, the only variation in Z is basically because of hydrostatics. So this is because of fluid weight. Yeah, because of fluid weight, just as in our hydrostatic type problem. Now, this is not always going to be true, right? So for example, if W was non-zero, we might have something that's a little bit more complicated. for dp/dz. But there should be some contribution from fluid weight as long as we're not ignoring gravity. But this just serves as maybe a reminder that now that we're considering fluid dynamics, or once we start considering fluid dynamics, we can have pressure changing because of the fluid velocity, that's described here by these terms, and captured by the Navier-Stokes equation.